This video is going to go through and review the integral applications that we have with parametric functions. You don't have quite as many applications with integrals. You see a lot with derivatives, but the integral is pretty limited, mainly working with arc length and distance traveled. And so that's what's going to take you through here. And then I'm going to finish with one that is a lot like what you see on an AP FRQ type question. So first one we have here is a particle motion. We have a particle motion where they already give you dx dt and dy dt. They're referring to you as it's the way we represent velocity because it's the derivative. And we want to write an expression for the distance traveled by the particle on the time interval of 1 to 5. And again, since it is particle motion, they would only be able to work with positive t values, a positive time interval. So our distance traveled is the integral from the starting t to the ending t, so from 1 to 5, of the square root of dx dt squared, so e to the 2t being squared, and dy dt squared, so the square root of 3t plus 1 squared. A lot of times you will see this squared out. I found this question as a multiple choice question, so they did go a little further to get the answer to look right, but not a lot. You're going to write it as the square root of e to the 4t when you multiply powers, and when you do this, the square root and the square cancel, 3t plus 1, and that's what you're looking for the final answer. When you're doing distance traveled or arc length, what you'll see a lot of times is they are the setup but do not integrate, or they're ones that they're in a calculator section where you would use your calculator and the FNINT function of your calculator to evaluate it, or it is something that is very simple to integrate by hand, and that has to be something that works out very nicely where you don't end up with the square root working in there and you can integrate it a little easier. Second problem is an arc length, so just getting comfortable with the way that it's worded. Here's the common wording for a problem like this. Find the length of an arc formed by the parametric equations, and again, they have to give you the interval. The only difference really between arc length and distance traveled is your time interval cannot be negative with particle motion, whereas when you're just finding the length of an arc, you can work with t values that are both positive and negative. The actual operations and integration is exactly the same. So in this problem, we are integrating from -2 to 1. I am going to have to find dx dt or x prime for this one and y prime. Dx dt would be 2, and dy dt would be a chain rule, power out front, power 1 less. Derivative of what's inside is just 1, so I'm going to write it as 1 over 2 square root of t minus 2. So when I have my integral, it will be the square root of 2 squared, which is 4, plus the square root, or plus the value of 4 times 2 or over 2 radical t minus 2 all squared. I'm going to square that out, but then after that I'm going to go to my calculator. So I have the square root of 4 plus, when I square this out, I get 1 over 4 times the quantity t minus 2, or you could distribute that through and say 4t minus 8. At this point, I'm going to my calculator. I'm going to use the FNINT button. I'm going to make sure that I use parentheses around this denominator, whether you have it multiplied out or left in this form. Either way, you have to have that denominator in parentheses. Go to your calculator, it'll give you the answer. You expect a lot of decimal answers with these because of the radical. You can either write it as 5.912, that's the truncated answer, or 5.913 is the rounded answer. Positive answer, it is representing a length, so you will only get positive answers for these. And then the last one, and this is kind of going into what we talked about with some of the FRQs from past AP tests. I really just took a past AP test and changed things around a little bit as far as the equations and the information that's given. You're going to see a question very similar to this on your quiz, asking you to take derivatives and use that to use integration to find the position. So what they tell us, we're working with positive time. T has to be bigger than or equal to 0. Again, it's particle motion. We know at time t equals 1, the particle is at a position of 2, 7. We're given the derivative of x and the derivative of y as a set of parametric equations. And we have to do two things. We have to find the x-coordinate of the particle's position at 4, and then we're going to find the y-coordinate of the particle's position at 4. So we're going to start with the x one, which means I need to use this equation. If I want to find position, I need to integrate. So I'm going to integrate 2 over t squared plus 3. My boundaries are going to be what I know and what I need. This should sound very familiar from last year's calculus class when we were doing the fundamental theorem of calculus. We know the time at 1. We know the position there. We want to know the position at 4. So my boundaries are going to be 1 and 4. And what's going to happen when I integrate this is I'm going to get the x-coordinate of 4 the position at 4 minus the position at 1. So that's what my fundamental theorem of calculus says. If I integrate x prime, or dx dt, from 1 to 4, I get x of 4 minus x of 1, the position at 4 minus the position at 1. Well, right here, you could integrate this by hand. It's an arctangent. It's really ugly. This is not a question that you'll be forced to do that, though. This question and many that you see on past AP tests are always in the calculator section. So you're going to use your calculator, use the FNINT button, and evaluate that definite integral with the calculator. I've already done it, so I can write down what you get. You get 0.737. We're looking for the position at 4. We know the position at 1 is 2. That's the x-coordinate of the position. I'm looking at the x-coordinate, not the y. So I'm going to put a minus 2 here. I'm going to add 2 to both sides. So my x-coordinate of the position at 4 is approximately 2.737. The next piece is asking you to do the exact same thing, but now we're defining the y-coordinate. So we're going to use dy dt, and we're going to use the information about the y-coordinate of the position. So it's going to start off very similar. We're going from 1 to 4 again because I know about what's happening at 1 and I want to know about what's happening at 4. We are setting up my integral as a cosine t. And when I do that, I'm going to get the y-coordinate of the position at 4 minus the y-coordinate of the position at 1. Again, cosine cubed, yes, you could integrate it by hand. It's a mess. You'd have to save a cosine and rewrite it with identities. It's not something that you want to go through unless you actually had to. Instead, we are going to use our calculator. You have to be in radian mode to get the right answer here. When you put that in your calculator, you get a negative 1.255 equals y of 4 minus, we know the y-coordinate at 1. It is 7. It was given to us up here. Add 7 to both sides. So we get the y-coordinate at 4 when I take negative 1.255 and add 7 to it as approximately 5.745. This is very similar to a question that was on AP test about 2 years ago. They asked other things, but I just really wanted to focus on this piece because this was a piece that I didn't mention in any other video with parametric, and you'll also see something like this on your quiz. So now, looking at your videos, hopefully by now you have watched the first parametric video, which was the pre-calculus, eliminating the parameter. The second one was all about the derivatives and the applications of derivatives, and then this third one looking at integrals and integral applications.